There is a theorem on your geometry course that can be used to construct a tangent to a circle at the given point on the circle. State this theorem and use it to construct a tangent to the circle shown at the point P. A tangent to a circle is a straight line that touches the circle at just one point on the circle. So this straight line just intersects the circle at this one point called P. Now, the theorem says that if we take a line from the center of a circle, so this is the center of this particular circle, to the point of contact of a tangent, that is from C to the point P, then this line is actually perpendicular to the tangent. That's the theorem. I guess it's not too surprising that we get 90 degrees. So if we want to construct a tangent that to the circle at the point P, well, we could imagine trying to draw it just by placing a ruler so that we can try and draw a line that just touches the circle at this point. Well, that's not a very good way of doing it. We need to use the theorem. What we should do is draw a line, a straight line, from the center of the circle to the point P. And then we need to draw a line that's perpendicular to this radius CP at the point P. One way to do that is to use a ruler and a set square. So we would line up the ruler with the radius CP of the circle. Then we would place the set square on the ruler and position it so that we can draw a line through the point P. So that will ensure that this line here through the point P is perpendicular to the line CP, to the radius. Then what we can do is we can just extend this line here on the other side, and that's our tangent. Another way to draw a line through P which is perpendicular to CP is to first of all extend the line CP to the point Q and make the length of CP equal to the length of PQ. You can just use a compass to step out the length CP out here. So CP will equal PQ. Then what you can do is get the perpendicular bisector of this line. The bisector of the line will pass through P, and the perpendicular bisector of the line will be the tangent at P. To construct the perpendicular bisector, what you do is get your compass, and set it to a distance that is greater than CP, that is greater than half the length of CQ. Make an arc with the compass center point at C. Make this arc here. Make another arc on the same side with the compass point at C. Then, with the same extension on your compass, place the point of the compass at point Q and make an arc here which cuts this arc, and then make another arc which cuts this arc here, and then just join up the points of intersections of the arcs, and it should pass through P. This is the perpendicular bisector of the line CQ, so it'll pass through the midpoint of CQ, which is P, but it will also be perpendicular to CQ, which means that we will have the tangent to the circle at point P. In the diagram, the line L is a tangent to the circle. Find the values of x, y, and z. Now, an important theorem that is used here is the theorem about the angle in a semicircle. Let's suppose we have a semicircle, that's half a circle, so that this line here is a diameter, passes through the center of the circle. If we pick any point on the circle and draw lines from that point to the end points of the diameter, then this angle here will be 90 degrees. And it doesn't matter which point we pick on the circle. We could pick this point here and draw it, connect it to the end points of the diameter, and we'll have a right angle, and so on. So this is an important theorem. It actually comes from an earlier theorem which states that the angle at the center of a circle, in this case it would be 180 degrees, is twice the angle at the circle and standing on the same arc. So if this is 180, this here is 90. So it comes from a more general theorem about the angle at the center of a circle. But anyway, I won't go into that here. Just remember that when you have a semicircle, then the angle in the semicircle is 90 degrees. So you can see that x is 90 degrees because this is a diameter of the circle. This dot here represents the center of the circle. So we have a semicircle. Now we have two angles inside this triangle. If we know two angles, we can get the third angle. We can get y degrees because the three angles add up to 180 degrees. So y is 48 degrees because 42 plus 90 plus 48 equal 180 degrees. Now what about z degrees? Well, we can use the result of the previous part. Since L is a tangent to the circle, and this is the point of contact, then a line from the center of the circle to the point of contact is perpendicular to the tangent. So in other words, y plus z must add up to 90 degrees. So z has to be 42 degrees because 42 plus 48 degrees equals 90 degrees. The circle A in the diagram has center A and a chord CD. A chord is just a line that cuts the circle at 2 points. We're given that AE, this line here, is perpendicular to CD. If AE is equal to 3 and CD equals 8, find the length of the diameter of the circle. Now we use an important theorem here. The theorem says that if we draw a perpendicular line from the center of a circle to any chord on the circle, so AE is a perpendicular line to the chord CD, then AE will bisect the chord. It will cut the chord in half. So if the length of the chord is 8, then the length of CE must be equal to the length of ED must be 4. Half of 8 is 4. But notice that the line from A to D is a radius of the circle. A is the center, D is a point on the circle. And notice that we have a right angled triangle formed here. And we have two short sides of the right angled triangle. They're 3 and 4, so we can use Pythagoras to find the longest side, or the hypotenuse. So we see that AD, by Pythagoras theorem, must be the square root of the sum of the squares of the two short sides. This is the square root of 25, which is 5. That's the famous 5-4-3 right angled triangle. So if the radius is 5, it means that the diameter is 2 times 5, which is 10. The circle in the diagram has center O. The distance of O from BD is 4. So what does this mean here? It doesn't mean O to B is 4. It means we want the distance of the point O to the line BD. Well, that's the shortest distance of a point to a line. The shortest distance of a point to a line is the perpendicular distance of the point O to the line BD. So this distance here is 4. We are also given that the distance of O from the line DC is 3. So the perpendicular distance of the point O to the line DC is 3. We want to get the length of the diameter of the circle. We want the distance of B to C. Well, since BC is a diameter and O is the center of the circle, we can see the distance of B to O is equal to the distance of O to C. So we can put a tick on each of those. In a previous example in this video, you saw that the angle in a semicircle is 90 degrees. Well, here we have an angle in a semicircle. See, this is a semicircle, diameter BC. This angle up here is the angle, it's known as the angle in a semicircle actually. This angle is 90 degrees. Now, to find the diameter, we will consider similar triangles. We have, and look at corresponding sides. We've got some similar triangles in this diagram. Let's take the big triangle. That's triangle BDC. We know we have an angle of 90 degrees up here. Actually, this side BC is the diameter. I'm calling the radius R. That's the distance of the center to B. And you can see we have two radii here. So the diameter is 2 times R. Let's call this angle in here X. So here it is in the big triangle, and it's also part of this smaller triangle, PBO. You can see this side is R, and PO is 4. Let's call the angle here Y. So here it is in the big triangle DBC, and here it is in the smaller triangle QOC. So straight away you can see that triangle DBC is similar to triangle PBO because two of the angles are the same. We have a 90-degree angle and we have angle X is the same. That means that the third angle must be the same. So we'll just change the color here. So the third angle here must be Y. And similarly here, we can see that these two triangles are similar to each other. You see, we have two angles that are the same. If two angles are the same, then the third angle is automatically the same because the three angles add up to 180 degrees. So we have three similar triangles here. As a matter of fact, all we have to do to answer this question now is to look at these two triangles. These two triangles are similar, or equiangular. The angles are the same. But they also have a side that's the same. This side is the same in both. This side is called R, which we don't know yet, but it's the radius of the circle. So we have an angle side angle situation for both triangles. We have the angle X, the side R, and the angle Y in this triangle. We have the angle X, the side R, and the angle Y in this triangle. So we have angle side angle situation for two similar triangles. So this means that the triangles are actually congruent. So we have congruent triangles. Congruent means that the two triangles are the same in every way. So in particular, that means that the corresponding sides are not only in the same proportion as any other pair of corresponding sides, but the corresponding sides are actually equal. So the sides opposite angle X are the same. So if this is 4, then this side here is also 4. And the sides opposite angle Y are the same. So we have another pair of corresponding sides here. So this is 3, which means that this here must also be 3. We can use Pythagoras Theorem to find out what R is. So R is the longest side. That's the side that's opposite the 90-degree angle. So by Pythagoras Theorem, R squared equals 3 squared plus 4 squared, or R equals the square root of the sum of the squares of the two short sides. We get 5. So this here again we have the famous 5, 4, 3 right angle triangle. So R is 5, which means that the diameter must equal 5 plus 5, which is 10.